Yeah. Okay. Okay. That's the only one. Okay. Okay, then welcome back, everyone. Thanks for the opportunity to give this class here. So I'm basically continuing what Yahoo started, and he did a lot already. And so I just first, before I go on, I want to give you an idea now. I mean, he showed the equation of states and everything, and how the structure of the neutron star looks like. And so the outer part, as Yahoo said, is basically iron, but then as you go in, somehow the density increases and you get heavier and heavier nuclei. And the outer crust, that's what's called the low neutron drip. There you have basically nuclear ladders and an electron fluid or an electron gas, basically. That's still pretty weak. But then at some point, these nuclei become so heavy that they're not stable anymore, and that they cannot maintain so many neutrons. And the neutrons will drip out. That's called neutron drip, and you get a fluid of neutrons. And then you have kind of lattice of nuclei immersed in a fluid of neutrons and electrons. And at even higher density, so this is, say, neutron drip is at 4 times 10 to the 11 grams per centimeter cube. And the inner crust, then, okay, this is all debatable where something starts, because we don't know exactly, the physics there completely, but that's roughly maybe a 4th times what's called nuclear saturation density. I'll talk more about this. This is 2.8 times 10 to the 14 grams per centimeter cube. Gigantic densities, right? Remember, iron is a few grams per centimeter cube. Here we're talking about 10 to the 14 grams per centimeter cube. If you go even further in, then the density gets so big that you get gigantically big atomic nuclei that then cannot even, because you have a competition between the repulsive electric forces and somehow the surface tension of these nuclei. And the preferred state is then they're not even spherically symmetric anymore, but they start deforming. And these are called pasta phases. And, so they then continue maybe until half-time saturation density. And everything inside, that's what we call the core of the neutron star, and that's a liquid. So somehow the most outer part, and this here is a kind of a realistic picture, depending on a realistic equation of state. Somehow everything that's red, that's the core of the star. And that's basically everything. That carries most of the mass. And then you have this eggshell layer, that's the crust. That somehow is then made out of matter at lower densities. But most of the stars at extremely high densities, and it's a liquid. Okay? And so that's what I mainly will talk about my talk, and it's kind of like a continuous transition, as you see. So these pasta phases kind of take you continuously from something that's solid to something that's really kind of roughly continuous transition. Right, and so what I want to mainly talk about is what's inside, right? What's the stuff at the center here, where the question mark is. And we kind of know that this here is neutron matter, as Yahoo's discussed, neutrons, protons, electrons, muons maybe, and maybe some other complications. But we have no idea really what's inside at the center. But that's interesting because there could be completely novel forms of matter, anything different than anything we've seen anywhere else. And so that's interesting. So the question is, what could there be? And so you can start from the standard model and the particle content it has. And so in the standard model, you have quarks, these are these guys, and everything we know is made out of an up and down quark, but they're heavier quarks. Now, in a neutron star, you have an upper limit of energy or density and chemical potential, and the maximum chemical potential in a neutron star is of that order. 1.5 GeV. And the reason is simply, if you put more energy in too small volume, it will simply collapse. There is a limit. No one knows exactly where that limit is, because it depends how rich that matter is, how much it can withstand gravity. But there's definitely a limit. And so you cannot have any particle that's in the standard model. And so they're, for instance, heavier quarks, but they're far too heavy. Their mass is bigger than this. And so we don't expect them to have anything else. But there could be this additional quark, the strange quark, which has a mass of around 100 MeV in vacuum. That could be there. So there could be something called strange. On the other hand, there's the electron, but it also has a heavier cousin called the muon, which is also around 100 MeV. And also there is enough energy in principle in such a neutron star that you can have muons, and they will arise at a sufficiently high density. In addition, this is somehow the quark level. We know in nature there's confinement, and instead of these quarks, what we see are neutrons and protons. But you can also have all kinds of heavier so-called baryons, say systems made out of free quarks that are color neutral, and there's a whole slew of them, right? And there in particular some particles called hyperons, and they involve these strange quarks, right? So the neutron proton only involve up and down quarks. They involve strange quarks. They're heavier, but they're light enough that they could be present in a neutron star. And so that's just scratching the surface. There are all kinds of particles that could be there, and we don't really know what is there. In addition, there are neutrinos, but usually, as the was already discussed, they escape. In addition, these are the forces in nature that we have. And, Yavuz already mentioned some of them. What I want to point out here is that all these forces, the electric force, the strong force, surely gravity, and the weak force, are important to describe that neutron star. And that's different than basically any other system in nature, because everything else, okay, you have an atom, but you can then say, okay, that's my building block. Yes, you need all these forces to form the atom, but then I go on and describe everything with just electromagnetism, right? Here you really need all forces to describe the basic aspects of that matter. And that's what makes it a bit challenging. Okay, so what could there be? And as I said, there are many particles, and what can even happen that at high density, I'll say more about this, is that we see these bound states or confined states, baryons. The densities are so high that these baryons actually don't even have space anymore. What could happen is that they dissolve, right? I mean, all the structure that we had before, nuclei and so on, or anything else, are already dissolved. Say, interior of the star is boring. It's a liquid, no structure anymore. And it could happen that the same thing holds for these baryons, that they just overlap, dissolve, and form quark matter, where these quarks are actually free, and they still interact with each other, but they don't form baryons anymore. And so there are kind of two classes of what could be inside. There's hadronic matter, and there's the confined quark matter. And in both cases, there are many options. On the hadronic side, okay, this would be the standard case, standard NPE, neutron, proton, electron, muon matter. That's kind of the basic model. But you could have all kinds of complications on top. These nucleons can become superfluid. I might say more about this. They can be transformed into heavier baryons, these hyperons, while these weak interactions that involve strangeness, say why, there could be other hadrons, so-called mesons, pions, or kaons. They could even condense, and so there are just many possibilities. There are excited states of these baryons, of a proton, for instance. They could be present at these really high densities. Lots of options here, because there are many of these hyperons, and you could have any kind of composition involving them. On the quark side, it's in principle simpler, because you only have free quarks, but they come in free colors and with two spins. And so there are many ways for them to what's called condense. What you can do is, I mean, these particles are fermions, and you can take two fermions, and fermions, as Yavuz nicely explained, they don't like to be in the same state, right? They pile up and form these Fermis, see, right? Every guy has its own state. But what you can do is you can take two fermions and form a bound state. And if you combine two fermions, which have spin 1/2 particles, you get an integer spin, right? So you form a boson. And these bosons have a completely different statistic. They follow the Bose-Einstein statistic, and they can Bose-condense. They can all go to the ground state and lower the energy dramatically. So that's what can happen, and that's in the case of quark matter. Here it's called superfluidity. In the case of quark matter, it's called color superconductivity. And there are many ways in which these could happen. For instance, what you could have is you could have superconductors that are crystalline. They are kind of like a solid that, basically where the condensate varies in a periodic way that acts like a solid. You can have anisotropic phases where there's a preferred direction in space, and it's not isotropic anymore. You can also have something called kaon condensation that's similar to this on this side, but it's something rather different. It just has the same name. You can have mixed phases where you have, for instance, both quark matter and hadronic matter consisting, or anything we haven't even thought about, right? And so there are dozens of possibilities that we already know, and probably equally many no one has ever thought about, right? And so there's a lot that can happen. And so the question is, how can we then understand what's going on? And so if we know what's there, say if we have, for instance, these particles or the hyperons or whatever, then we can ask, well, how much is there of each particle? And that's basically what Yavuz already did. And so I just very quickly skip over this. As I said, it's the weak interaction that can convert particles into each other. And then you have to look for chemical equilibrium. What's the preferred state, the preferred concentration of each of them? And well, he already nicely showed this, and so I don't want to go into too much detail, but I want to show you this. Now we have even more particles, right? For instance, we have what I call here X. Oh, let's start simple. Okay, we have neutrons, right? Ideally, you would say, okay, well, protons at these high densities, if they get very close, there's a very strong electrostatic repulsion between them. Right? And so you would say, okay, well, let's not have protons because the neutrons are cheaper. But as soon as you start piling up more and more particles, and you have to pile up a lot of particles, right? I mean, this is this exclusion principle. Every particle goes in one state, and you fill higher and higher energy states. And in a neutron star, we have to somehow accommodate of the order of 10 to the 59 baryons. And so you pile them up, but at some point you realize, well, it's actually cheaper now to actually add protons because you already piled up these neutrons to such a high energy. And so even though there's a repulsion between them, you will have some protons. But then if you have protons and the star wouldn't be neutral, I'll get to that, it will just be blown into pieces. The electric force is so much bigger than gravity. So you need to neutralize the star. And so for each proton, you also need something negative, typically an electron, or at high density, a muon. Okay? So that's the standard state status. But if you have now anything exotic that I call X here, you have other ways to kind of somehow distribute that baryon number. You can start filling from scratch again, and the first particles always are very cheap. Or if you then pile up to high energies, it gets expensive, right? And so what nature does, it distributes this to go to the lowest energy state. And so if you have many particles here, somehow you can lower the energy. That's what typically people call softening. That will make the equation of state, the pressure, rise slower with density. So that's the generic thing. On the other hand, and I'll get to that, that's not the whole picture, but this is only taking into account that these particles don't interact. Whereas in reality, they interact extremely strongly. And so, right. So that's just just a picture. You distribute them, and Yavuz already showed this. You can then look for chemical equilibrium, and you get relations like these that in these reactions that transform particles like these here, you then have the sum of the chemical potentials initial and the final states have to match, whereas this only involves the degenerate particles, say no neutrinos. Okay, you need charge neutrality. That's the number I wanted to show you. You might remember this from electromagnetism class. At 1 Fermi distance, the electric force is 10 to the 38 times bigger than the gravitational force. So you really need the star to be neutral. Otherwise, it could never exist. Gravity could never bind the star. Right, so you need charge neutrality. And so you need it over sufficiently small regions. But actually, since it's so dramatic, you effectively basically need local charge neutrality. That means the charge density has to be 0. Okay, then you have a few say equations, and these equations, for instance, in case of neutrons, protons, electrons, and muons, these equations that I showed you, this is the relation that Yavuz already showed you what the density is in terms of the Fermi momentum, but there's one additional ingredient. You also need the what's called dispersion relation or energy momentum relation that relates the Fermi momentum and the Fermi energy, the chemical potential, right? And that's where the strong interactions come in. So that's exactly what we don't really know. So this here would be the ideal gas relation, right? The Einstein relation. But in reality, this is some function that we just don't know. Right? And as we'll see, the interactions are dramatically important. So yes, one gets to some extent, one can describe some things this way, but if you want to do it quantitative, you need to know what these interactions are, and we don't really know that. I'll get to that later. Okay, so Yavuz already gave you a lot of exercises. So okay, I have it on my slide, but I don't really enforce this that you should do this. Yeah. If you don't have strong interactions, the maximum mass of a neutron star is 0.7 solar masses, right? So we couldn't explain any of the stars we see. Okay, so the common folklore is it's the degeneracy pressure that stabilizes a neutron star, but actually it's more the strong interactions than it's the degenerate pressure, right? Because we see now stars that are more than 2 solar masses. You need extremely strong repulsive interaction that do that. That's true. Yeah, there you have electrons. Electrons don't care about a strong interaction. Okay, let me go on. Okay, and then you can, for instance, do this. And so this is what you get typically. The problem is, again, this. We don't know this precisely. And so it depends on your model of the interactions. And you can have very different results. So for instance, this considers that you might have hyperons, and then you get curves like this, that these hyperons at some density come in. And which comes in first depends, because that also depends on the interaction. Each of these will have such an energy momentum relation, and they are not the same. It depends on the particle type. And in particular, even if you take the simplest formula, Einstein, then these masses won't be what they are in vacuum. In a dense medium, the effective mass decreases, and we don't know really how big they are in a neutron star core. Yeah. Yeah. No, unfortunately. No. Right. So that means it depends on your model, and the composition is still very uncertain. Okay, right. So Yavuz already mentioned this. A neutron star is very hot, right? I mean, they emit in ultraviolet X-rays. That means they have surface temperatures of, well, nearly a keV, actually hundreds of electron volts or something like this, that means they're very hot on human standards, or if you compare with the surface of the sun. And their core is even 2 orders of magnitude hotter, because the most outer part of the neutron star strongly insulate heat. But then again, to actually judge this, you have to compare to the say characteristic energy scale of that matter, right? And it's a strongly degenerate system. And the question then would be, how much energy do you have to provide to change that system, to somehow melt that condensate? And that energy is of the order of the chemical potential, which is a GeV, right? And so I just want to kind of point out how dramatic this is. This is one of the coldest systems we have in nature, because this ratio T over mu is 10 to the minus 5, 10 to the minus 4 at most, probably even smaller for some sources, for most of them. And that means this is as degenerate as it gets. So if you saw the smeared out formulas, that's what if you really zoom in. I mean, this is as good a step function as it gets, right? I mean, this tiny temperature has no effect. It looks very like this, hard cutoff. And so, but that's good because we have a small quantity, T over mu, which is tiny. And that's interesting because, I mean, I won't talk much about this, but this is what I mainly do. And so at least want to mention it. What I'm interested is, I want to know what's inside. And I want to know how can we figure out or get signatures what's in the interior, right? And so there are 2 kind of quantities you can look at. There are bulk properties, like the mass, like the radius, moment of inertia, compressibility, things like that. They are all determined by a single function, the equation of state that you was already mentioned, right? So how does density depend on pressure, or sorry, the other way around? Any function between 2 thermodynamic variables is an equation of state. If you know that, you can compute all these quantities. The problem is they hardly constrain the composition. And the reason is that they are already, the equation of state is strongly fixed by astrophysical constraints. So no matter what it is, the star has to have a certain resistance against gravity. And there's very little room then. And the uncertainties, I'll get to that we have are dramatic. We don't know what's inside. And they basically all can give you exactly the same. They can give you the same star within the uncertainties on the interactions that you don't know. And that's why it's really hard to determine something just based on these quantities. On the other hand, there are dynamic material properties. This is something, if you kind of perturb that system, if you slightly bring it out of equilibrium and then ask what happens. Right? And these are things like viscosities, transport coefficients, emissivities. And while the equation of state is basically an integral over the entire Fermi sea, these dynamical material properties, they would be 0 if you would have a perfect Fermi gas at 0 temperature. You wouldn't have any of these properties. You only have them because you have this tiny temperature. Because what it does, it gives you a few degrees of freedom above the ground state, excitation, quantum excitation above the ground state, that then can transport things for you or do anything dynamic, right? And so, well, you can, in principle, yes, right, exactly. But the point is, these quantities depend on T over mu, typically as a power law, right? And if you're in different phases, you have different degrees of freedom, right? And so you then can get different dependencies on T over mu, right? And so if you have different compositions, and so for instance, you have 2 phases that deviate by 2 powers in T over mu, that's a difference of 10 to the 10 between these 2 phases for such a quantity right there. And so you have a chance to distinguish something, even though we do astrophysics and everything is messy and there's so many uncertainties, right? If you have differences like 5 orders of magnitude, 10 orders of magnitude, that's dramatic. And so there is a chance using these dynamic properties to distinguish them. Okay? And so there's a huge potential there in principle. It's just hard. And so you need to look for processes that can kind of push that star out of equilibrium, that does something to it, and then it has to relax back to equilibrium, or anything dynamic. And so there are quite a few processes that can actually do it. For instance, you can look at the cooling of young stars or the cooling of accreting sources that Yavuz already mentioned, that are heated in low mass X-ray binaries. They probe the neutrino emissivity. And so you have an observable from spectroscopy, the temperature that you can link this with. That will tell you something about the interior because the neutrino emission happens in the core of the star. Similarly, you can look at stellar oscillations. You can look at pulsar glitches, something people here do. There are lots of, or you can look at neutron star mergers, either in the spiral or the merger, and all these probe certain properties of the interior. And if you can link them, the observables that you have in these processes, you can learn something about what's going on inside. And so, as I said, that's what I'm mainly doing. I just want to mention it, but I won't have much time to talk about it from now. Right. So the problem, as I said, is there's this force, the strong nuclear force, and as the name says, that's extremely strong, and it somehow gets bigger and bigger the closer to particles get. And so the underlying theory that describes all this is called quantum chromodynamics, and it's an incredibly successful theory. And it has a particular property, namely that's called asymptotic freedom, that if you go to really high energies, then that force becomes weak. Okay, and then you can basically compute the answer to all kinds of questions you have. What's the cross section for this or that process? And it works like a charm, right? That's what people do at CERN, and it has been spectacularly successful. The problem is this coupling depends on the scale, and if you go to very small scales, it gets big. Okay, and that's the problem. So here you basically have quarks and gluons. If you go to small scales, the degrees of freedom change, right? You kind of form a string of so-called glue in between that these quarks can never escape anymore, and you form baryons, neutrons, protons, things like that, and that's called confinement. That happens when the coupling gets very, very big. Now, in a neutron star, that's the problem. We are still in a regime where the coupling is kind of big, but it's not dramatically big anymore. And so it could be that we are in a regime where what's called deconfinement happens. And so let me go to this. So as I said, usually quarks are confined into baryons and mesons, and so if you bring a lot of energy in the system, as I said, it gets kind of perturbative. You can describe things, but that would be at very small distances, right? You describe very short distances, everything is simple. But as these particles, these quarks go away from each other, you kind of have a string between them. You have an interaction between them that gets the bigger the distance is. So you know this kind of from a spring, right? You have a linear force law. The further they're apart, the bigger the distance, right? And so what happens at some point is that you have so much energy that what you can do is, in a quantum theory, and Einstein tells you mass is just another form of energy. So you take that energy and produce more mass, more particles, and that's what you can see here, right? So these strings then break, and all you get is effectively new particles. And all these small tracks here that you see in a detector at CERN, thousands of them, are just mostly pions. You create tons and tons of new pions from this effect. And well, we see that, we can probe that. But at really high density, that theory predicts that this confinement stops. And at very high density, where the interaction gets weak, you have something called deconfinement, and you have free quarks that then might still interact, but are not bound into hadrons anymore. The question is, no one knows where this happens. And it could be that in neutron stars, that's the only place, or the early universe, in the early universe, we kind of know this must have happened at some point. And the only place right now is neutron stars, where you could have something called quark matter that is not made out of these baryons that we see everywhere around us, but out of free quarks. Okay, so you could think, okay, well, let's check, let's take the theory and solve it. And it turns out it's very hard to solve that theory. theory. But nonetheless, even in this regime here, where the coupling gets very weak, called the strong coupling regime, people can solve it on supercomputers, and they have ways, statistical ways, to then solve this theory numerically and get an answer. The problem there is that nice method that can explain everything by now. You can compute what's the mass of a proton, what's the cross-section for this process or that. You can even compute properties of light nuclei by now, which is quite challenging, but you can do it. Completely fails at high density. And that's just a computational problem, right? So at high density, we don't have any numerical method or any method at all to solve the theory. And that means we don't really know what's going on. We cannot solve the theory and get answers from first principles. No controlled QCD prediction for neutron star matter. And that's unfortunate, but it means right now the only way to learn something is use astrophysics. Because astrophysical observable can constrain what's really there, and it's going to help us. Even if theory cannot, from first principle, tell us what's going on, to figure out how does matter at really high densities behave. And in general, this is described by the equation of state. Yavuz already nicely explained all of this, and he showed you these two limits. I just quickly want to introduce the convention. You can have a general classification. So, say a polytropic index of 5/3. That's what you have for non-relativistic matter. That's kind of the baseline, the standard case. And you would then call anything that has a polytropic index bigger than 5/3, and harder equation of state. It's really hard to compress it because it provides a lot of pressure. Everything that has a polytropic index smaller than 5/3 would be a soft equation of state. Okay? And so surely the harder the equation of is, the bigger neutron stars can you form, the more can that pressure withstand gravity. Right. But as I said, there you can at least get a qualitative insight from the qualitative behavior. Quantitatively, we cannot solve anything, but what we know is that the nuclear force has a characteristic behavior. It's attractive at long distances, and it gets very repulsive at very short distances. Okay, and so you then have a sweet spot here in between, and that's exactly why we have stable baryons. That's why we have stable nuclei, because these two forces kind of balance out, and you have a sweet spot that's called nuclear saturation density, a particular density where energy is the most energetically preferable state. Okay, and that's the density that you reach in heavy nuclei. Okay, and that's the density that if there wouldn't be gravity, maybe also a neutron star would be in, but gravity compresses it even more. And so you go to this regime where things get strongly repulsive, right? And so then you get extremely repulsive interactions that can stabilize that star even much more than a degeneracy pressure can. Right. And so then, since we don't have a nice theory to really describe this from first principles, what one needs to do is one has to do modeling. And one simple way to model this complicated interaction between quarks, which is a colored interaction, the charge of the strong interaction is called color. And what you can do is you can say, okay, well, over long distances, we have this confinement and then no long-range colored interaction. Similarly, similar to what you have in atoms, right? Two atoms are neutral, and if they're far away, there's no interaction between them. Only if they're really close to each other, then you feel still an interaction. It's the same thing here. And so the long-range part of this, you can somehow describe by exchanging color-neutral bound states, and that would be something we call a meson. Right? Exchange particles in nature are always bosons, and these mesons are bosons. And so the long-range part of the nuclear force, that's something we know, is determined by the exchange of the lightest particle, which is the pion. Okay, so that's one of the few things we really understand. But the problem then to come up with such a model of the equation of state is twofold. First of all, we don't know the interactions that well, because we can't solve the theory. And another one is just complexity. There are many, many particles. right? If there are not just two particles that interact, but there's another guy over here, another guy over here. They all interact with this one guy, right? And you have to solve this many-body problem. That's also extremely challenging. And so that's what people face who want to then model this. And it's really not simple, okay? So at nuclear saturation density, this density in nuclei, we can do experiments. That's where we can kind of engage these models. Do a lot of experiments. And for instance, we have data on masses of nuclei, right? The whole nuclear chart. And we can use that to kind of fit these models. We have elastic scattering of particles. We have even inelastic scattering at higher energies. We have excitations of these nuclei. They can oscillate, they can rotate, they have all kinds of states, excitation states, and all this can be used to constrain the interactions and the equation of state at saturation density, at that particular density. But then again, a neutron star is at much higher density, and there we don't know that much. And then you need to do modeling, and probably, okay, since I'm running out of time, I shouldn't go through all of these. There are all kinds of models. Let me point out one, and it's called chiral effective theory, because that's kind of a controlled approach. That's the low energy theory of QCD. You can prove that, and at very low densities, this is a controlled approximation. And so, because this is basically fixed by the symmetries of QCD. And so at very low energies, we know what's going on, right? We know at saturation density what's going on, and we can start extrapolating. Right, so that's what I want to say about interactions. Let's talk quickly about what kind of stars we can have. And Yavu showed you the equation of state, the Tolman-Oppenheimer-Volkoff equation. Right? These are very complicated equations that you need to solve numerically. Let me take a really broad brush and simplify dramatically, and we'll see that we can learn something. What you can do is, instead of looking at the Tolman-Oppenheimer-Volkoff equation, which are differential equations, you just replace derivatives by fractions, and you average these quantities. Okay, so that's what I do. If there's a pressure, I say, well, that's the average pressure in the star. If there's the energy density, I say that's the average density in the star. And if there's a derivative, I say, okay, it's just a ratio of these two quantities. Right? So I end up with a really simple equation, this one. And then I know what the equation of state is for different forms of matter. You said, as you showed, in the general non-relativist matter, the pressure goes as a density to the power of 5/3. And so if you insert this here and solve this equation, you get exactly what you showed you, that the mass goes as 1 over the radius cubed. So the bigger the mass, the more compact is the source. Okay, so that's the standard case. That's what you would have in hadronic neutron stars, where you have heavy hadrons that are non-relativistic. Right? The mass of these is much bigger than the kinetic energy. If, say, in heavy white dwarfs, somehow where the pressure comes from is not the baryons, but the electrons, and they are light, and they have high energies, and so you get this here, that the energy density still comes from the nuclei, but the pressure comes from the electrons. And if you solve this, then that's exactly the instability that Yavu showed. You get that the mass is constant. That shows you something is fishy here, right? The mass should depend on the size of the system, and that exactly signals that instability. You can look at another case, and that's completely relativistic matter, where both the energy density and the pressure stem from the same light particles and are relativistic. And then you get this behavior, that the energy density and the pressure goes as density to the 4th power, so they're kind of proportional to each other. And if you insert, you get the mass is proportional to the radius. Okay, and so we'll see that. Well, exactly, one can actually will find that asymptotic case. And finally, there's a really weird possibility, and that's that we kind of live in a metastable world. That the absolute ground state of nature is not these baryons, neutrons and protons that form atoms and everything we see, but that the actual ground state is quark matter. Okay, and that would mean that if we would perturb our universe, would give it more energy, you can go over the hump and go to this lower energy state. Okay, so you have a metastable minimum, you're trapped there, but if you can tunnel through or somehow get enough energy, you can go to a lower energy state. That's called the strange matter hypothesis that Britain came up from here. And if you do that, what you get is that the energy density is basically constant. So in this case, you would have, relative to our ground state, a relative energy density. And from this behavior, if you plug this in, that the energy density is constant, you get the most simple mass radius relation you can think of, namely what we are used of from objects like this. And the reason is that also there, the density is kind of constant for these atoms that we used to, and then you get something like this. But this is the most extreme case that you can think of. Okay, and now then you can check, well, what do we actually get if you numerically solve this TOV solution? You get something like this, similar to what Yavuz showed you. Somehow, the smaller the radius is, the bigger the mass. And so here, you indeed get exactly this 1/r³ behavior, somewhere up to here. And here, eventually, it becomes constant and then turns around and the star becomes unstable. And okay, Yavuz showed it. If you wouldn't have interactions, the heaviest neutron stars would be 0.7 solar masses. We see neutron stars that are significantly more heavy than 2 solar masses by now. That's this other case of a strange star, right? Which is really the ground state of nature is different, and you get something like this. You would get this relation, m goes as r³, and in this case, the star would be basically self-bound. You wouldn't even need gravity. It would be self-bound because the pressure from the vacuum outside, which is a different vacuum that star has, would compress the star, right? And then only before it shortly before it becomes unstable, gravity would come in and then bind that star, and eventually, not even this is, it will shrink it up. Finally, there can be hybrid stars, and also here, indeed, you find this asymptotic behavior. A hybrid star is a star that has an outer part that is made of ordinary neutron matter, but somewhere in the center, the density is high enough that you can have some exotic form of matter, for instance, quark matter. Okay? So if you have something like this, you get a behavior like that this here is kind of the hadronic part that goes when the mass goes as 1/r³. This here is that determined by that core, and you get that the mass goes indeed linearly with the rate. Okay, so somehow you can learn the qualitative aspects of what can happen already from a really simple analysis. I mean, if you want to do it quantitative, you have to solve the TOV equation and really work it out how big these numbers are. Right. So what constraints do we have from astrophysics? So in particular, when it comes to masses, radii, how big are these sources? The best way is if you have neutron stars, in particular pulsars in a binary, because then you can do pulsar timing and you can ask, well, a pulsar is basically, say, a cosmic lighthouse that has a beam and it rotates with a certain frequency. And it does this everywhere on the, say, its orbit. Okay, and so that basically, if you look at these pulses, they will come in a bit later if it's going away. They come in a bit earlier if it's going towards you, and so from this you can basically reconstruct the orbit of this binary system, and can then determine, and then that orbit to leading order will depend on something called the mass function. Say in the Newtonian case, it depends on this combination of the companion mass and the neutron star mass. If you want to know more, I mean, if you have a way to determine what a companion mass is, by other ways, then we can determine what a neutron star is. PSR means pulsar. This would be a pulsar, and so that would allow us to determine this. If you can do even better observations, if you go to include general relativity and do something called a post-Keplerian or post-Newtonian expansion, there are 5 more parameters. I mean, say in the simplest case of Kepler, you have 5 parameters. If you go beyond that, there are 5 more that would come in if you start expanding and take into account relativistic effects. Okay, and for instance, one effect is that this binary would lose energy by radiating gravitational waves. That would be one of these parameters, and others that, for instance, the perihelion precession of Mercury that you might have heard about that have been confirmed. Many of these parameters, if you can measure them, you can pin down. If you have 2 more, you can pin down the mass precisely. Okay, we are not there yet, but this gets better and better, and at some point, hopefully, people will be able to do that. Another way, and that was a big thing, say, 15 years ago, people can look at systems that are basically where you have a neutron star and a companion, and the neutron star has a pulsar beam. That pulsar beam is reflected in the gravitational field of the companion. Okay, and so that pulse takes a detour, and you see this here. It takes a bit longer once it's somehow aligned with that companion, and you can measure that effect. It's a purely general relativistic effect. You can predict what you expect, and you can determine this way the mass of that object. And that was the first time that people could, in a very precise way, then determine what the mass of a very heavy neutron star is. So there are neutron stars, there are 2 solar masses, and they could pin it down very precisely. Okay, by now there's another one that was done this way. I apologize, that's a kind of old plot. I couldn't find, I'm sure there are better ones by now. But there was another really important development, and that came with time-resolved spectroscopy. So on many of these neutron stars, you have a hot spot, right? And there the star is rotating, and you see X-ray pulses. Okay, and if you then can do spectroscopy and have time-resolved spectroscopy and see how the spectrum changes, you can basically determine what the size of that hotspot is and what the size of the star is. Okay, and that was a big breakthrough with this NISA on board of the ISS, and people could pin down the radii of, well, several neutron stars very precisely. So that's what they find. They find that for 1.4 solar mass star, you get something of the order 11.4 kilometers, but still huge uncertainties. For 2.1 solar mass star, you get an even bigger value. But, within uncertainties, they're perfectly consistent. But what this tells you is that the mass of the star basically does not change, whether you're at 1.4 or at 2.1 solar masses. If quickly going back to that plot here, that's exactly what you expect from the TOB equation. There is a regime where basically the radius is independent of the mass. Okay, and it seems we're still in that regime. Okay, and what this tells us is that the equation of state must be very stiff. And already that we see neutron stars that have 2 solar masses mean the equation of state must be dramatically stiff. Another thing where we got new insight was from neutron star mergers. The last few orbits of these neutron stars, people could measure how these stars, when you get very close, tidally deform. Okay, and so this gives you another insight, namely that it's possible to deform them. They could measure that effect, and it gets you basically opposite bound. Right? These other results told you the equation of state has to be sufficiently hard, otherwise they could never exist. This tells you the equation of state cannot be too hard because otherwise you couldn't deform it. And so you can constrain the equation of state kind of from 2 different sides, and that's very useful because you then have 2 different bounds that tell you what's going on. I mean, this is all complicated. I don't have time to go into details here. There's another thing you can do, and that's from the theoretical side. As I said, we know not much But we know we have a controlled theory at very low density, and we have a controlled theory at very high densities. At asymptotic densities, the interactions get weak, and you can do what's called perturbation theory. Okay, but the problem is this is at ridiculous densities, not at neutron star densities, but density 100 times where you can actually do it. But you can then ask, I mean, the equation of state is one function, right? It might be complicated. There might be phase transitions. There might be all kinds of things. But there's another thing that helps, and that's causality. And that's what Yavuz already mentioned. We know that the speed of sound can never be bigger than the speed of light, right? And that means the slope of the equation of state cannot be too big, okay? And if you do this, and if you then take different, say piecewise, say equation of state, say parametrizations, where you take into account that the speed of sound cannot be bigger than 1, they can get a bound, right? Because you cannot have arbitrary abrupt changes. So that's what they get. They want to match at the highest densities that are completely unphysical, but still, there we know what's going on. They want to match at low densities where we know what's going on from current perturbation theory. And then they can interpolate with these guys. And so that's kind of, to some extent, controlled. We don't know. I mean, if you have do this rigorously enough, that the speed of sound cannot be bigger than 1, that's a pretty strict constraint. And so that's what they find. They can constrain the equation of state theoretically from these two sides. Okay, so effectively running out of time. So I also wanted to talk a bit about black holes, but I guess, can I get 5 more minutes or should I stop here? Yeah, okay. Okay, so this is something that was already mentioned. In principle, you already find black holes in Newtonian physics. You get exactly the Schwarzschild radius, the simple escape velocity argument. And this was not long ago. But okay, then Einstein came along, and and Schwarzschild came, and he realized you can get a solution to Einstein's field equation in vacuum if you take into account that you have spherical symmetry. Right? And so what you find is that in the end of the day, you end up with a really simple form of what that metric, the solution of the Einstein equation, is for such a spherically symmetric mass configuration. And this here only holds outside of that mass configuration. And that's called a Schwarzschild metric. And what appears here, 2MOR, that's exactly the Schwarzschild radius that we had before. That's basically the point where nothing can escape. If you're at that point and you send the light ray straight outwards, it will never get to you. Okay, and if you're inside, there's nothing to know about what's going on inside. But this simple metric describes the space-time around any massive object. And if the size of that object is smaller than a Schwarzschild radius, then you form a black hole. Right? Every system has a Schwarzschild radius in principle. And black hole is a very simple object. In this simple approximation that it's static, it's described by a single number, its mass, its total energy. That's all there is. And then you have in size the Schwarzschild radius, which is roughly 3 kilometers, times the mass of that object in solar masses. And so for different objects, you can then ask how big is that? And for instance, for the Earth, the Schwarzschild radius is not even a centimeter. So it's basically a marble ball. If you shrink the Earth to the size of a marble ball, it will collapse to a black hole. But it's much bigger, so it doesn't really play a role. But nonetheless, the Schwarzschild metric describes the space-time around of the Earth, or around any static object. Okay? And so just quickly to go through this, I mean, first of all, nothing dramatic. It looks like things would diverge here, and in the end, the world is over at a Schwarzschild radius. If you look at this closely, you can find other coordinates that you can even describe what's going on inside. You can just never learn something about what's going on inside, and so it's always kind of a bit speculation. But as you know, we have by now nice pictures of black holes. People took photos, And that basically comes from because there's an unstable circular orbit for light at 1.5 times the Schwarzschild radius. So if you put a light ray right there at 1.5 times the Schwarzschild radius, it will circle forever. But if you put it a slight bit away, it will go either out or in, right? And so that's what people see there. You have an accretion disk that illuminates the black hole, and then you have light that goes around the black hole a few times until you see it. Right? And so that gives you these cool photos that you've probably seen. When you look at massive objects, then the innermost stable circular orbit is at 3 times the Schwarzschild radius. So there you need to be quite a bit further away to have orbits. And it turns out, even in general relativity, Kepler is right. You get exactly the same orbits. Okay, so these are the pictures that I'm sure you've seen. If the black hole is rotating, things become more complicated. And then you get another solution of Einstein's field equations without matter, and that's the Kerr solution. So if you have angular momentum, if the star rotates, there's another quantity that describes such an object, and that's the angular momentum, or typically the rotation parameter G over M. And that quantity is kind of limited. You only get a nicely behaved solution if that rotation parameter is not too big. At some point, you get weird stuff like naked singularities and things like that. So there is what's called an extremal Kerr black hole. That's the limit to get a sensible black hole that we can kind of comprehend. And so that's what you get. I mean, you do the same thing. You look at a solution of the Einstein equation now, including angular momentum, and you get this. You get a slightly more complicated metric that somehow reduces to Schwarzschild in the case A goes to 0, but there's one qualitative difference. You have a mixed term now. I mean, if you compare this to Schwarzschild, you would only have, say, in the metric, you only have terms like dt squared, dr squared, and so on. Now you have a term here, dt by d phi. Okay, and that's crucial because that term here, first of all, you only have it, you see it here, is proportional to A if the star rotates. But if you then ask, what's the geodesic of a light ray in angular direction, right? So I say, okay, dr is 0, d theta is 0, only define dt are non-zero. And then I have a light ray. For a light ray, it's on the light cone, ds squared is 0, right? And so you get this equation. So if this term wouldn't be there, you would get a standard case that we always have. It doesn't matter in which way I send a light ray around the black hole or around any object. It just rotates with the same angular speed. What you get here, because of this term, this has two distinct solutions. That means that light ray goes with a different angular speed this way than the other way. So the only way to reconcile this, surely, the speed of light is that the entire space-time around that object rotates. It's not static, but the space-time around that object rotates with it. And the closer you are to the object, the more it rotates. As you go to infinity, it's slower and slower, but as you go to the surface of that an extremal black hole, it will basically rotate with the speed of light. Right, and this effect is called frame dragging. And right, an interesting thing there is I mean, first of all, the event horizon of such a Kerr black hole is smaller, right? Everything you see here is kind of inside the event horizon of a Schwarzschild black hole, but there's then a region, I mean, and the horizon, the whole black hole is smaller, this yellowish thing is the horizon, but then there's a region around called the ergosphere, and that's a region where space-time rotates so strongly that there's no way to go the other way, right? Any object will have to rotate with the black hole in exactly one direction. Okay, and that's called, as I said, the ergo region. And in principle, you can have more complicated black holes. You can have another conserved quantity charge. A black hole could be charged, but then again, neutron stars, I told you, cannot be charged. No objects in the universe is in any way substantially charged. And so you can have more solutions, but basically astrophysics not that relevant because there's no way to form these objects. Okay. Okay, I'm running out of time, so I guess I skipped that. I just quickly want to, this is my last slide, point out that the interesting thing about black holes astrophysically is what happens around them. We have no idea what's going on inside, but the space-time around them is extremely interesting. You have an accretion disk, as we discussed, as we heard this morning. Sorry, you have gigantic magnetic fields driven by the accretion disk. The black hole itself has no magnetic field, but you have charges there that rotate and they create a magnetic field. You can have jets then, charges that are accelerated in a magnetic field, all kinds of things. And so that's why black holes are interesting. What's going on around them? And I guess we'll hear a lot about this in other talks this week. Okay, thank you so much.